That's me. Thanks for inviting me to this beautiful school. Okay, my topic is just a little bit different from the previous one. So we are moving higher and higher in the atmosphere, and we are going in the space. And my two lectures have been divided into two different aspects. The first one is much more propedeutical in order to introduce the problem, and tomorrow will be much more technical, dealing with the turbulence and other aspects like complexity. Okay, so this is the outline, and I would like just briefly introduce to all the students the concept, the problem related with the high latitude ionosphere, so the structure of the high latitude ionosphere, and why this is the importance of a high latitude ionosphere in terms of a more general aspect, the Sun-Earth relationship, because they are connected. We have a big system from the Sun through the solar wind to the magnetosphere to the ionosphere system. And then I will just introduce some of the most relevant aspects of the magnetosphere-ionosphere coupling, so the convection, the field-aligned current systems, and the aurora. Now, everybody knows that the effect of solar UV radiation and X-ray on neutral atmosphere can generate ionized elements. And so we have these elements can essentially create a population of a standing population of ionized atmospheric constituent, and that is generally called ionosphere. Regarding the Earth, the ionosphere is essentially that part of the atmosphere which is completely ionized or partially ionized, and it consists of free electrons and ions of different species. And in the case of the Earth, it's extended generally, so you have to take these numbers not as exactly, extends from 60 kilometers in the atmosphere up to 3-4 Earth radii. Because when we go outside, we can, in the equatorial region, we found what is generally called the plasma sphere. This is an image, a picture of the plasma sphere, which is essentially made by hydrogen, ionized hydrogen, so protons. Now, what are the? Oh, I have just put a few equations. Please don't take care about these things. But it's very simple. How can we how can we explain how we can form a ionosphere? So we can consider, for instance, the density, the electron density, and we can express that the variation of the electron density, the rate variation of the electron density is generally due to a production rate, Q, a loss by recombination, and also loss by drift motions. Now, the main three recombination processes for the ionospheric electrons, for instance, are due to radiative recombinations, and this is one example for the oxygen. And the other one is the dissociative recombination, so this is another example, and this is one of the most important in terms of the most relevant one, which essentially acts in terms of loss in the ionosphere. And the third one is the attachment, so generating different species. So we have these elements, this mechanism for electrons. And if we consider a very simple atmosphere, so isothermal, plane and parallel atmosphere, and we consider the solar ionization rate and the recombination rate independent on the wavelength, we can construct a model, neglecting the drift velocity, in which we can just imagine what is the profile in the age of a ionospheric species. In this case, this is called the Chapman layer. And we can see that just going from the ground in the ionosphere, we can see that we have a maximum density at a certain age, specific age. So this is the expression, the mathematical expression. By the way, there are some elements that can change. It depends on the zenith angles, as you can see here. And also it depends on various factors that can change under the conditions. Clearly, real ionospheres have much more complex structures and than the simple Chapman layer. And this is due to the fact that Chapman requirements are not fulfilled. For instance, the isothermal condition requirement is not satisfied. And the recombination processes assumed to be proportional to the square of the density of the electron density is better described in the higher level to be proportional in terms of a direct proportion to the density. Furthermore, in some layers, we have to consider also the vertical diffusions, which generating the mean density profile. So this essentially means that we have to consider another term. We have thermal diffusion and drag force. And if we put all together, so we have this is the thermal diffusion coefficient, this is the drag force coefficient. So if we introduce all these terms all together, we get better profiles. And these are the profiles that we can observe in a real atmosphere. These profiles depends, for electrons in this case, depends from the local time. And this is crucial. So we have something that is changing in local time. We have a daytime profile. So when we when we look to the sun, we have a higher ionization effect. So the density is very higher. When we go to the night side, we have a reduction of this. And then also the effect of the solar cycle. So this is one of the first elements that we have to keep in mind when we want to discuss the Sun-Earth relationship. So ionosphere is important because this is also linked, is completely linked to the solar activity. And okay, if we consider all the elements like ionization recombination with all the species, the thermal heating, the transport, and so on, we can see that the real ionosphere is much more structured. So we have different layers with different specific features and physical features. And we generally can divide the profile of the electrons, for instance, identifying different regions, the D regions, the E region, the F region that is then subdivided into other two regions, and the outer ionosphere. And these are the main characteristics. This division is made clearly by the maximum that you can see. This is 1, 2, 3 layers, and so on. So and this is the last one layer. So you have 4 different layers at least, and sometimes also more and more, depending on how much finer you want to investigate some profiles. This is for electrons. What happens if we look, for instance, to all the other species? So we have completely different profiles. This is electron profile, this is the oxygen plus profile, this is the protons profile, this is the nitrogen plus, and so on. So each species has a different profile. Clearly, when we go farther and farther, the most light species you can find, and they generally generate the so-called plasma sphere, which is made essentially by protons, ionized hydrogen, and so on. Now, the ionospheric medium, so it's made by a plasma, and with a certain percentage of neutral, especially in the lower layers. So it is a plasma, and as a plasma, it can respond to electromagnetic disturbances. And in particular, the ionosphere is at the same time a sink and a source of particles. A sink because it receives particles from the interplanetary medium, through the solar wind, and from the Earth's magnetosphere that can precipitate, especially during geomagnetic substorm or magnetic storms in the high latitude ionosphere. At the same time, it has been clearly demonstrated in the past that it is also a source for oxygens, for also helium plus, which escape from the ionosphere during very intense geomagnetic substorms and storms, populating some current structure that flows in the Earth's magnetosphere. This is one example of the fact that if we want to understand the physics of the ionosphere, we cannot separate, consider the ionosphere independent from other parts. The ionosphere, the solar wind, and the magnetosphere, they are all one system in some sense. They are all connected. Now, as I was saying before, the high latitude ionosphere is a part of a more complex system. Solar wind, what is the solar wind? Solar wind is essentially the plasma which flows out from the solar corona in the heliosphere. So it's the expansion of the solar atmosphere. And is made by plasma. It essentially consists of 98% of protons and electrons, and then we have other species, and like alpha particles and minority ions. Then we have the Earth's magnetosphere. What is the Earth's magnetosphere? The Earth's magnetosphere is the space around the Earth where the Earth's magnetic field, so the one that is generated by the geodynamo, is confined by the solar wind due to, in terms of fluid effect, magnetofluid effects. And the third term is the Earth's high latitude ionosphere, which is completely magnetically connected to different regions of the magnetosphere. In this framework, the polar and auroral ionosphere is an element of the solar terrestrial energy coupling. And so we have to understand that many of the physical processes we observe in this region are related with what happens in the magnetosphere and what happens in the solar wind. This is one example. Oh, sorry. Let me go back. Okay, should start. I don't know why that doesn't start. Would you like to start? No. Okay, I'm sorry for this. I can see if I can try it again. No, it doesn't like. No, it doesn't like. Let me check in this way if it works. Here it works. I don't know why. So this is a very clearly, this is a movie. We have a coronal mass ejection from the sun. This coronal mass ejection impacts on the Earth's magnetosphere, just compressing and also transferring energy, particles, and moments to the Earth's magnetosphere, which is advected to the high latitude ionospheres. So the study of the high latitude ionosphere is completely connected with what happens in the solar wind and in the sun. So we cannot separate these things in order to understand the physics of the ionosphere. Now, okay, I want just spending some few words regarding the high latitude ionosphere, which is completely different from the middle latitude one, because it is influenced by energized particles coming from the sun and from some regions of the Earth's magnetosphere. And we have, in some sense, to understand that the overall dynamics of the Earth's magnetosphere in response to the solar wind and interplanetary conditions changes is also another cause of the dynamical changes that we observe in the high latitude ionosphere. And this is due to the fact that we have electric fields and currents that directly connect the ionosphere to the magnetosphere. Now, I would like to present some of the effects in the next part of this talk. So I would like to discuss of one special kind of field of currents which directly connect the ionosphere to the remote regions of the magnetosphere, which are called the field-aligned currents, and other processes. Now, this is a sketch of the solar wind magnetosphere-ionosphere system. So we have the sun, that through the solar wind impact on the magnetosheath, which is just the boundary of the Earth's magnetosphere. Then we sometimes, under a specific condition that I will discuss later, we can have what is called the day-side reconnection in front of the nose of the magnetopoles. So when we have this phenomena, we have transfer of energy from in terms of particle, momentum, and so on, from the solar wind directly inside the Earth's magnetosphere. So we have this transfer of energy enhances magnetospheric convection and other processes that generally occurs in the tail regions, in the night side tail regions of the Earth's magnetosphere. And all these impacts on the ionospheric outflows, and all these have impact on the ionosphere to the magnetic field line. You can see that the magnetic field line, for instance, here are directly connected to the high latitude ionosphere. So particles move along magnetic field lines. So what happens here has a direct impact here. What happens here or on the boundary has a direct impact here, which is called the cusp, and so on. So we cannot discuss what happens here without considering what is happening outside. This is one sketch of what I was saying before. The solar wind, the interplanetary magnetic field, which is just advected in a frozen field condition by the solar wind, can be sometimes can assume different BZ components. So the Z component is the one that is orthogonal to the ecliptic plane, or the Sun-Earth ecliptic plane. So if we have solar wind in the north component, here we have that also the geomagnetic field, the magnetospheric field, has the same direction, and in this condition there is no possibility to connect the external solar wind with the external magnetic field with the internal one. Conversely, when we have a southward component, it is possible to have a merging from the external solar wind, from the external interplanetary magnetic field, and the Earth magnetic field inside the magnetosphere. So in this situation, we have that the plasma can flow inside, be transported in the tail region, or directly connected to the high latitude regions, and then coming back from the tail to the ionosphere. So we have mainly two different main pictures. These are pictures. This is not reality because I am only reporting the B south component, but the reconnection at the day side, the reconnection is influenced also by the BY components on the ecliptic plane. So these are the two, and differently from one on the other, we have different effects, different impact in the high latitude ionosphere. So in terms of precipitating electrons, if we confine to the high latitude ionosphere, which is generated by UV radiation, another element that has to be included are electrons that directly precipitated due to the link that I've shown before. And these electrons precipitate in different regions. If we look to the high latitude ionosphere, this is strongly structured, and we can recognize specific regions. And these specific regions are each one directly connected to a different region of the magnetosphere of the solar wind. In particular, we have the dayside Cusp region here, which is directly connected to the solar wind through the magnetopause. The other part is the auroral oval. This is the region where it is much more, there is a higher probability to observe auroral events. And this region is directly connected to the inner part, to the closed field lines that connect that region of the ionosphere with the tail region or the dayside magnetosphere. And then inside we have a polar cap. So the particle precipitation in this region is completely different because it depends on the physical properties of the plasma to which they are connected. This is a much more complicated scenario. So if you look to this is an image of the Earth's magnetosphere. If you look to this image, you can see that you can recognize a lot of structures. All these regions are characterized by different features in terms of density of plasmas, in terms of temperature, and so on. For instance, the magnetic lobe, which are this one, the density of plasma is is of the order of 10 to minus 3, 10 to minus 2 particles cubic centimeter. So it's an empty space. While if we go to the plasma sheet in this region, this is called, the density is about 0.11 particle per cubic centimeter. And so this region is generally imagined as a place where plasma is stored, is convected and stored inside the magnetosphere. And then it can be released and so it can reach, it can get the high latitude ionosphere. The other important point that I would like to stress is that all this system, you can see in this system there are a huge amount of currents. There is a current flowing on the magnetopause. There is an internal currents on the equatorial plane, which is called the ring current, which is directly related with the storm, magnetic storm. Then there is the cross-tail current flowing in this direction. Then there are field-aligned currents connecting the different regions to the ionosphere. The auroral over-precipitation is characterized essentially by two types of electrons. Electrons from central plasma sheet, which is this region here, in the tail, in the night side sector of the tail region, and electrons from the boundary of the plasma sheet, which are the last closed lines. And they have different impact, and they produce different phenomena occurring in the high latitude ionosphere. For instance, these electrons, they have an energy of a few kiloelectron-volt, and they produce essentially diffuse auroras. The electrons from the boundary, they generate discrete auroras, and they have an energy which is much more small, about 100, not seconds, sorry, but electron volt. And they are accelerated then by the electric field that are aligned to the magnetic field lines in the auroral regions. Here you can see a very simple sketch. So you have the central plasma sheet region that is connected by magnetic field line, and so particles can move around this. Then when they get to the mirror point in specific conditions, they can go inside the ionosphere, or sometimes due to some different energization processes, so they can penetrate inside the ionosphere. And these are directly connected to the inner regions of the magnetosphere. The one coming from here, they generate a completely different kind of aurora, the so-called diffuse aurora of polar rain. They can generate polar rain here. They are connected directly to the tail region, to the lobe of the magnetosphere. This is an example of the enhancement of the luminosity due to auroral phenomena. Now, day side cusp electron, they are completely different. They are characterized by very soft spectra. So the energy is about 10 electron volts. And sometimes they can get also energies up to 1 keV, but this is the higher limit that you can find. These are essentially thermal particles. And the origin of this is essentially the Earth magnetic sheet, which is just that layer outside of the magnetopause, in front of magnetopause. So the particles that directly come from the solar wind, they can enter to reach this region. Then which is the polar cusp. Then we have the polar cap, which is characterized by electrons of thermal energy of 100 electron volts, and is associated to fluxes which are 2 or 3 orders of magnitude smaller than what we observe in the auroral oval. And in these regions, we have a specific phenomenon which is called polar rain. So this continuous flow of particles coming from the tail regions, essentially, they are considered polar rains. Sometimes they are accelerated by other phenomena, and sometimes there is an increase, so we talk about polar showers instead of rain. Now, when the interplanetary magnetic field Z component is southward, there is another effect, which is essentially due to the reconnection between the interplanetary magnetic field, which is transported by the solar wind, and the magnetic field lines related to the geomagnetic field. You have that these field lines are just transported through the boundary of the magnetopause, and then they are transported back towards the sun, and they generate a global large-scale convection electric field. And this large-scale convection motion transport plasma essentially runs in this way, here, in this way. It generates two cells. The convection cells are represented by an electric field, assuming that this can be a non-rotational field. So you can see that essentially the plasma flow around the auroral oval and then goes back in the polar cap. Okay, and so this movement, however, is strongly dependent on the condition of the Y component of the interplanetary magnetic field, because depending on the Y component that can be on eastward, on westward, on the solar eclipse, you have that the position of the dayside reconnection point moves, and so the cell that you generate are distorted in one direction or the other. This is an example of the two cells. And one important aspect is that when we have southward IMF, and so in the presence of a steady reconnection at the nose, the flow pattern of the plasma is this one. In the northward condition situation, we have a reversal of the flow pattern. And this is due because the reconnection occurs in a different way. So in this case, the flow is completely reversed, depending on what happens in one situation on the other. Okay, let me show you how this convection cells depends on the different conditions. You can see here that depending on the Y direction, this is the different plots are the results of a long-standing observation using the superdual auroral radar network. And depending on the different configuration in the YZ plane of the interplanetary magnetic field condition, you can have the formation, you can observe the formation of two cells that changes. This is in a perfect southward condition. You have a very strong cells, and then they move completely, and they disappear when you have northward one. So this is an example of how much the convection pattern in the ionosphere depends on the condition of the solar wind, magnetic field. This is, I'm sorry for the picture, but this is very small. So here you have, this is, in this plot we report an example of a turning of the magnetic field, the external magnetic field you can see here, BZ component, from the northward to the southward component. And what happens to the cells in time when the magnetic field turns to southward. An important point that I would like to stress is that this image is 1 every 2 minutes, so the process is extremely fast. You can see how the convection cells changes, so everything is extremely fast and dynamic. And so the ionosphere responds promptly in a very rapid way to what occur outside in the solar wind. This is something that it's very important. So we cannot have we don't have a standing high latitude ionosphere. because this is a consequence of the fact that the external magnetic field, so the interplanetary magnetic field, is continuously changes, and the condition of the solar wind is continuously changes. So we can talk about a mean ionosphere, but we cannot talk about of an extending ionosphere. This is an example of motion. This is made using swarm data, 2 years of swarm data. These are the two cells reconstructed by the magnetic field parallel component as measured essentially by the swarm satellites, and you have the cells, and simultaneously for this condition, AE is an index that is a measure of the magnetic disturbance level in the high latitude ionosphere and the high latitude regions. So for a disturbed period, you can see that these are the cells, and you see that there is an extension of this density of plasma. This is called the high latitude tongue of ionization of electrons. This is the electron density that is transported inside the ionosphere. So everything is very, very fast. And another crucial element in order to discuss the coupling are the currents. And so we have the so-called field-aligned current, which allowed plasma to flow into and out to the ionosphere. So these are responsible for plasma coming inside, so essentially electrons, and electrons flowing outside, also ions flowing outside. So the condition is this one, and we can recognize different current systems. In particular, we have the so-called region 1 field-aligned currents that originate near the magnetopoles. They are this one. Then we have the region 2. Then we have the Cusp, which is just another one that connects this part here. And then we have the Substorm current wedge, which originate essentially from the equatorial diversion, from the diversion of the equatorial tail current flowing in the magnetosphere, and this is active during substorm times. So, as a consequence of this current system, we have particles, electrons, and or other species plasma that can go inside and outside the ionosphere. This is another sketch. And we can recognize the region 1 and region 2 here, region 1 and region 2. And also we can recognize the Cusp. This is a very old. This is the Cusp precipitation. This is an example of the currents that flows in the magnetosphere, in the high latitude ionosphere. And this is a reconstruction of the same that is done using data from many satellites, if Ørsted, Swarm, Ampere, and CHAMP, I believe, not Ampere, CHAMP, Ørsted, and Swarm. And we can recognize the two structures, R1 here, which is the same, this is an old picture, R0, which is the Cusp precipitation, and then we have R2, 1 and 2. Okay. I don't know if does it work. We try again. It seems that works. This is a reconstruction of what happens by a model of the intensification of the currents in the high latitude ionosphere of this field-aligned current. So you have a huge amount of energy that is advected inside the ionosphere through this current system. Okay, another important aspect of this current system is the Substorm current wedge, which directly connects the tail regions, the plasma in the tail region, to the high latitude ionosphere, generating the so-called westward electrojet. That is something that enhances during the substorm, geomagnetic substorms, which are disturbances that you can observe on the Earth of the magnetic field, and generating also aurora event. So, and this current is due to the collapse of the equatorial tail current, which is disrupted, generating this wedge. It's the shape of a wedge, okay, and of currents connecting directly the tail region to the high latitude. But I would like just to show you that in this case, the processes are very fast. Here you can see the geomagnetic index, A index, which is a measure of the disturbance, of geomagnetic disturbance due to the enhancement of currents flowing in the high latitude ionosphere during geomagnetic storms. You can see how much faster is the dynamics. This is taken every 1 minute, and it is a comprised of two phenomena, essentially. The directly driven, which is the enhancement of convection. You can see here you have enhancement of convection that generates an enhancement of the energy which is transferred to the ionosphere. And then the loading-unloading processes that occurs in the tail, which appears in terms of burst of activity. This is something that is very interesting, because if we study these events, these activity bursts, we have found that these events are, in terms of energy, they are distributed according to a power law. So this means that these processes are scale invariant. And this is something that is extremely crucial in order to understand the overall magnetospheric dynamics, which in this sense is termed to be critical. Now, the field-aligned currents, as I said, they are channels for delivering electromagnetic energy into the ionosphere. And we can measure this energy in terms of field-aligned Poynting fluxes. So a field-aligned Poynting flux allows us to measure the energy which is transferred to the magnetosphere, to the ionosphere. And this is an example of Poynting flux reconstructed using a crossing of a satellite. If I remember correctly, this is the MSP satellite. And you can see that there is a energy flux that is going downward, so it is transferred directly to the Earth's ionosphere. And the effect of this is essentially we can divide into two terms. The first one is a Joule heating rate. So these processes is also an element that can heat the ionosphere, that can transfer energy. So then heating the ionosphere means that we can, through other processes, we can heat the thermosphere. Because I'm discussing about the ionosphere, but the same region are part of the thermosphere. So we cannot divide these systems. So we have to talk about an integrated system, atmosphere, ionosphere, magnetosphere, all global. And so the energy content influence that comes from the magnetosphere due to the connection with the tail regions of the Earth's magnetosphere, the energy coming inside, then it is dissipated inside the ionosphere. So it can participate also to other coupling phenomena with the thermosphere and with the atmospheric other processes. The other part is spent essentially in increasing the energy of the neutrals here, in terms of kinetic energy of neutrals. Just to show you an example of this heating, this is the change of the electron temperature observed by a statistical study made using swarm. And you can see that you have a clear increasing of the temperature in the region of the auroral oval. So where we observe the major part of the precipitation coming from the distant region of the Earth's magnetosphere. I don't know if this works, so let me now move to the last topic. I think that I am quite in time, which deals with the auroral displays. Another phenomena, another effect of the coupling between the magnetosphere and the ionosphere is the light emission that we observe during so-called geomagnetic substorms or auroral substorm. And these are the auroral display, which are essentially an effect of the particle precipitation in the high latitude ionosphere that occurs during substorms and storms. As a consequence of this particle precipitation, we have a light emission, and that is due to the excitation of neutrals. Essentially, oxygen is one of the most important elements that produce the auroras. And so another important point is that the auroras can show different structures. And this is impressive because this means that we have still not a single scenario to describe the coupling between the magnetosphere and the ionosphere. And we can observe essentially shapes containing, like in this case, not in this one, ray structures. They are essentially isolated rays, draperies on corona, or homogeneous arcs like this one, and bands. The altitude where the mean altitude where we observe the emission, the light emission, is about 130 kilometers. And these are the shapes. We have different shapes for the aurora. The homogeneous arc, the arc with the ray structures, the homogeneous band, the band with the ray structures, then rays, straight rays, or corona or draperies. So all these shapes are related with different filamentations of the currents we have in the high latitude ionosphere. So to study the coupling means to understand the formation of these structures. These are very complex structures and dynamical structures. This is a difference in the emission in terms of, this is a satellite that just crossing, measure the emission, the light emission. You can see that this is the part due to the diffuse aurora, while these are the discrete aurora generated by stray, ray or things like this one. Okay, what are the most important species involved in auroral emission? They are essentially the oxygen and the nitrogen, the molecular nitrogen. And in terms of physical process, it's very difficult to understand why we observe this line. Because these lines are generally due to transition, forbidden transition in terms of physics for the quantum physics from one state to the other. And so they are transition between what we call in metastable states, atomic states, or molecular bands. And, but this is important because otherwise we are not able to see this light. So we can imagine that in the first part, you can, when you have just electrons impacting on atoms, you can populate all the states. Then in the first few microseconds or less, you have a collapse to the metastable states. So after this, you generate a large population, a large extending area of this species that is in the metastable state, and then collapse later altogether, just generating the visible lights. This is something that is very crucial for understanding these processes. So the most common line are the green lines and the red lines. These are the most famous and most prominent line. Although the most energetic line is the one related with the ionized molecular nitrogen. Here is the transition, okay? And because this line is directly connected, this emission is directly connected with the energy of the incoming electrons. If we measure the relative luminosity between this line and the other two, we can get an information about the energy of the incoming electrons in the high latitude ionospheres. And these are an example that you can of the transition you observe. Essentially, you have the green one, which is this, and then you have the red oxygen line, which is a doublet line. Okay. Now, I think that I can stop here, so we have 5 minutes for questions, and I have also included some references for people that are interested in approaching this topic. Thank you.
Any questions? Okay. Okay.
One question. You mentioned, for instance, one of the effects of the fill-line currents is that you have this Joule's energy transfer somehow to the thermosphere. So there is a connection between the ionosphere and the lower atmosphere somehow.
Yeah.
What other effects you may have that are connecting the ionosphere and the biosphere, let's say, where we live?
Okay, so one of the most important, tomorrow I will discuss about these things in much more detail, but what is the relevance to study these things is that particle precipitation in this high latitude ionosphere can generate patchy structures in terms of density fluctuation. They call patchy density electron structures. These are multi-scales, and they have a very strong critical effect on radio transmission. So we have these things in terms of impact on the human activity in some sense. They have a great impact in GPS and in positioning systems and so on. These are one of the consequences of what now there is a new discipline which is called essentially space weather. So which wants to predict in some sense the effect of the solar activity on the anthropic state. Another effect is also that, okay, I confined my discussion essentially to the connections, but you can have also high energy particle precipitations. So when you fly in that area, you can have also high energy particle that can have a big impact on the on humans flying there, on also species. We have also what we call the cosmic ray, but essentially solar cosmic ray, so energetic solar particle that can precipitate in that area, just creating problems, because these are particles, protons, and with an energy that is about 1 megaelectron-volts or more. So you can imagine how much effect they can have in terms of impact on cells or other things. So there is a great impact of this. In 2013, I believe, there was a panel of NASA dealing with the space weather and solar terrestrial relationship, the impact on technological states. And they included the ionosphere in a global atmosphere, ionosphere, magnetosphere interaction model. And they said that we cannot separate these things if we want to understand what happens and what are the impacts on the human activity and also on life or whatever you want, I believe.
Any other questions? Okay, we have time for questions, so don't be shy. If there are no other questions from the participants, I just have a curiosity. There have been some theories on the link between earthquakes and the magnetosphere. I don't know what your opinion of that is.
Why? I prefer to stay on the path. I'm not an expert, so I don't know I know that there are some results showing that they have found some signature of changes of high energy particle precipitation just some days before. But the physical mechanism still, to me, is unknown. So there are people talking about Whistler waves. So it's a special kind of waves. The one that generally you can observe in the atmosphere, in the ionosphere, as a consequence of lightnings. So these are the Whistler waves. But these Whistler waves can modify the loss cone of particles, energetic particles, and then can go down. So the real mechanisms should be something difficult. So you can have something that changes the conductivity and the generating electric field in the crust, I believe. I don't know. I'm not an expert on this. But I don't know. I cannot say. This is something that is under study. And there is also a mission by the Chinese Space Agency, which is called CAS, which is devoted to study this as a first, one of the first topic. And then there was also, I believe, some studies that have been done in terms of swarm measurements. But I have not a conclusive answer. I don't know.
Okay, thanks a lot. Yep, there's a question.
So are there any long-term changes that we can observe in the magnetosphere? Or are there any changes coming up, let's say?
Okay, so I treat only fast processes. You can also have long-term changes depending on the changes of the orbit around the 1 year. You can find that there is a modulation also due to the changes of these things, and other changes which are strongly related with the solar cycle. So the most effective is the 11-year solar cycle. So in reality, the solar cycle is 22 years because it's the magnetic solar cycle. Every 11 years, you have a solar magnetic field reverse. So the entire cycle is 22 years. But during this, every 11 years, you have an increase and a decrease of solar activity, what we call in terms of faculae, sunspots, or whatever you want. And this essentially has a direct impact because there is a different kind of plasma flowing out from the sun that it can impact the Earth. So we have an increase of solar flares on the sun, and so there is a different impact on the Earth's magnetosphere. So the main long term is this one. Then there is a semester activity or things like this one, which is related to the fact that the equatorial line, the magnetic equatorial line, in respect to the ecliptic line, is not exactly aligned. So you have something that is a sort of, they call ballerina shape for the magnetic equatorial line. So the Earth cross region with different features. So northward and southward, and so you can observe also impacts on this in this term. So, but these are long-term variation. The most critical ones are the short-term, because short-term variations are much more energetically, and they can have a greater impact on the human activity, in some sense.
Any other questions? Yep.
In atmospheric corrections for electromagnetic waves, for example, if you use radar, you're doing ionospheric correction. So is there any error that is induced by this short-term activity into the ionospheric correction models?
So I know that there are people that are trying to make some of this. It's not, these changes are very fast and localized in localized structures. In the latitude is strongly structured. So if you're talking about the IRI model, the density profile, for instance, for one species, it can change dramatically from one side to the other. you have a model which, what I've shown you in the first part, these are mean models. They can depend on the latitude, they can depend on the local time, but they can depend strongly on the activity. So I don't think that there is a model you can try to do something that is very, very simulations and making considering these things, just starting from a mid-average profile, and then you can modify whatever you want.